That's another thing. But you can read it just for what the MIT culture slide. This, I forgot to bring my magnet before. I told you this thing had different magnetism. So I brought my cow magnet. Anybody know what a cow magnet is? Midwest? Cow magnets, what are they for?
It's to make sure all the nails and barbed wire collect in one spot in the cow's gut.
That's right. You feed this to the cow. It's like taking a big Tylenol capsule, right? And you feed it to the cow. It's magnetic, and all those little pieces of metal that the cow might eat, you want them to collect there. And what happens to them there is they sit on this little magnet.
I thought that they just cut it out when they slaughter the cow.
Well, if it's carbon steel, it should just dissolve over time in the hydrochloric acid. You know, hydrochloric acid. Your gut is about pH 2, and it's hydrochloric acid. It should eat. It won't eat stainless steel. Well, it eats stainless steel very slowly. Well, certain types of stainless steel will. If it's magnetic stainless, if it's BCC type. But you're right, a lot of the stainless steel won't. But most of what the cow eats is carbon steel, and so a lot of it will just get dissolved and stuff over time. But it keeps it from going through other parts of the cow and tearing up the cow's insides, basically as I understood it, not being a farmer. However, you can see it sticks up top. I put it down here, it falls off, and you have to pass this around again. You can actually feel the difference in pull-off force as you go top to bottom on that thing, which I should have passed around last time. Okay, any other questions? Any other trivia? Today we're going to go through diffusion bonding. Okay. Now just to make you sick of this, we talked about the two things that inhibit bonding are surface roughness and contamination. And in cold welding, you use mechanical action and pressure to shear away those rough edges and to extrude out the contaminants and stuff. In adhesive bonding, we don't get rid of it at all. We tend to use liquids which flow between the rough surfaces, and we just bury the contamination. Now, diffusion bonding, we actually use heat. It's like cold welding, but we use heat to help get more contact area. So these asperities or mountain peaks become soft. And we're going to basically push it over time. I'm going to hold the pressure on there for a fair amount of time, and that's going to allow us to essentially slowly get rid of those mountain peaks and get a larger than 30% contact area because the stuff is slowly deforming. So you get higher contact area because the heat allows things to soften and start to flow over time. You get what's called creep. Remember, silly putty would change its shape over time, overnight, you know. Well, basically, you're holding the pressure. And typically, diffusion bonding times in traditional diffusion bonding may be 24 hours in a furnace. So it's just like you're trying to get it to the silly putty stage, if you will, to get rid of the surface roughness. What I've got here is actually a prototype for a diffusion bonding specimen for one of the airfoils for the inlet of the F-22 fighter. This was given to me by a student who had worked at Pratt & Whitney, and he had it. He decided I could use it more than he could. But basically, they took two titanium plates, shaped them, and then diffusion bonded them together. So this is like putting two pieces of bread together. And at these intersections here, if you look at it, it was kind of sharp notched machine because you basically have put these two together and diffusion bonded the titanium under heat and pressure. So pressure, and typically this is to deform the asperities. The heat also hopefully diffuse away the contaminants. So the temperature has two effects. It softens the asperities so they'll deform more readily. It also allows the surface oxides and other impurities, hopefully, to diffuse away into the bulk material. The pressure is there to deform the asperities and keep things in contact. The types of temperatures that we use, T of bonding, is less than 8/10 of the absolute melting point and greater than about 6/10 of the absolute melting point. What do I mean by absolute melting point? Well, the melting point of lead is 327 degrees centigrade, but that's 600 degrees Kelvin. I had 273 to 327. Lead has a absolute melting temperature of 600 degrees Kelvin. So I have to be, when I'm talking about melting temperatures here, I got to be in absolute values. And 8/10 of 327, or 8/10 of 600, I'm using lead because it works out to a nice round 600. And I can do 8/10, I get 480 degrees centigrade. But 480 degrees Kelvin as 8/10. So if I was talking lead, I'd be talking 480 Kelvin, and 6/10 would be 360 Kelvin. Well, 360 Kelvin, that's 73, that's 87 centigrade. So if I've done diffusion bond lead, I'd do 87 centigrade, at least 87 centigrade, and if I add 120 to that, I get 207 centigrade. Okay? So that's for lead. If I do nickel, nickel melts at 1660 or something like that centigrade. Iron melts at 1500. Titanium melts at around 1620 or something. I don't remember the numbers exactly. And I'd have to add 273 to each one of those and multiply by 0.8 and stuff. But the diffusion bonding typically only works in these areas. One of the reasons that, well, anybody can think of a reason why it typically won't work at lower temperatures. Even if I had perfectly clean surfaces of lead, if I stuck them together at room temperature, why wouldn't I get diffusion bonding if I held them there for 24 hours? Turns out the diffusion is too slow. I mean, the atoms actually have to move and integrate themselves with one another. And if you look at the diffusivity of lead in lead at room temperature, it would probably take me 2 weeks. Okay, I could do it, and in fact, people have had situations where metals have bonded together under ideal conditions when they're slightly warm under long periods of time. But if I'm trying to make this a production process, it's pretty expensive to even wait a day to do the bonding. You don't do diffusion bonding on automotive parts, not with a value of $2 a pound. You can do it on aerospace parts with a value of $200 a pound. But if you typically figure that a furnace to do this heat treatment, it's typically going to cost you an industrial furnace, half the size of this room, and maybe having vacuum for titanium and everything, is going to cost you about $1,000 an hour to operate. So if you got to do a 24-hour heat treatment, you got $24,000 worth of heat treatment for one load in the furnace. Well, you can afford to do that on aerospace parts if you got to make some complex geometry. How would you have made that geometry in airfoil? That's just a slice off an airfoil. That actual blade is going to be this long and have this internal cooling passage. You can't machine that internally. You can't forge it. How else are you going to make those pores? How else are you going to make it lightweight? Okay, you may have actually air cooling on some blades. In that case, it's probably one of the inlet compressor blades, so it's not looking for air cooling, it's just looking for lightweight. Okay, or how do you make it lightweight and keep the external airflow shape? You have to take stuff out of the inside. How do you machine something on the inside? You can't, but you can machine it on one surface, or one surface of two pieces, and slam them together and get the pores on the inside, right? You just made a lighter weight turbine blade, which is important because that could be worth $2,000 a pound in the engine. Okay, so you can afford that. Now there are automotive parts that you can afford to do a heat treatment of 24 hours. For example, they cast. Anybody ride a motorcycle here? Did I talk about motorcycles before? The motorcycle cylinders. You really don't want to be riding a motorcycle and have that cylinder blow up, particularly when you're sitting on top of it, right? It could be a bad day. And so the cylinders are so complex with all the cooling fins for the air cooling on the motorcycle cylinder. You've seen them, you know, chrome plate them, they look really neat and stuff. Well, they have to cast that. That's a cast structure. We all know that, I don't know if I told you, I told you before about the saying when I was a young student or a young faculty member, and Professor Palou was teaching his fracture class that something won't fail unless it's been welded. I told you that story, right? Well, Professor Russell, and today at noon we have his retirement lunch, but anyway, Professor Russell modified that. He said, welded or cast, okay? Cast structures tend to have larger defects on the order of some fraction of the size of the casting. Well, there's going to be pores in those castings. And so one of the things they do is with those cylinders, because it's a critical component, it has high stress on it, they actually put it in a hot isostatic press, which essentially they're going to diffusion bond this complex shape together. So I've got some cylinder with all its cooling fins. That's kind of schematic, right? But anyway, I've got this part, which goes all the way 360 around, okay, with its fancy cooling fins, and I may have some flaw in here from the original casting, some porosity or some inclusion or whatever, and I want to get rid of that porosity, and I want to bond everything tightly to the inclusion. So what I'm going to do is I put it inside a furnace, a great big furnace, which is a huge pressure vessel that will take 10,000 psi pressure of argon gas. So I fill this full of argon gas, pressurize it 10,000 psi. Of course, I got to put a top on the vessel, and I'll heat it up depending on the alloy. Now, this is an aluminum alloy for these things typically, and so I probably only have to go to 8/10 of the absolute melting point might be 800 degrees centigrade. So I'll heat this whole thing up to 800 degrees centigrade. In fact, what I'll do is I'll pressurize the argon at room temperature to about 3,000 psi, and then when I heat it up to 3 times the absolute temperature, okay, I get the extra pressure just by expansion of the gas, right? So I only have to have 3,000 psi argon pumps to get this thing hot and pressurize it. And what happens is that high pressure, this is called hot isostatic pressing. Was invented by Patel Laboratories right after World War II. And it just squeezes everything together. And so any pores or anything like that just get diffusion bonded together. Okay? The pores are buried on the inside, and so therefore the argon doesn't get inside the pore, and any pores will just get squeezed together in a diffusion bondable way, get rid of those defects, and now you can ride with confidence on your Harley. Okay? But in fact, Harleys do that. In fact, about 10 years ago, turns out the world's largest hot isostatic press was located right up here in North Andover, Massachusetts. Okay, which is about 40 minutes north of us. It was a 300-ton vessel. It had 10 to 17-inch thick steel walls. It had an internal working diameter of 5 feet, 60 inches. And they built it to be able to do turbine discs. Because now you're interested in cylinders. In fact, after they had the explosion up there, and I went up there, they had a whole set of Harley cylinders, okay, sitting there in pallets and stuff that they were going to process. But they also did turbine discs for jet engines, because those are also castings, many of them nowadays. They make them out of cast alloys. They can't even be forged, but they can be hot isostatic pressed. So they put a cylinder, a turbine disc in here, and get good mechanical properties, equivalent properties to a good solid forging by hot isostatic pressing, which in a sense is just a form of diffusion bonding those pores together. Well, it turns out they had a little notch on the outside here. They've done all their stress analysis. This is the world's largest, and in fact, it blew up in the middle of the night. It broke up into, it was about 300 tons, if I remember correctly. It broke up into about 60-some pieces. The main vessel was 200-some, 60, 70 pieces. Anyway, the average weight of the piece was like 3,000 to 5,000 pounds. It was about 5,000 pounds, if I remember, okay? In fact, one of the pieces, well, the biggest piece, which was about 16,000 pounds, which had the primary fracture, landed a quarter of a mile away. Okay, it was still in the industrial park. It was 3 a.m. Nobody got hurt. Another 5,000-ton piece landed right on the operator's chair, but he had just gotten up a moment before it changed his chart paper. Okay, he had been sitting there 5 seconds before. He was sort of rattled after that event. Okay? But it was sort of an interesting explosion. But you got 15,000 psi in a volume that's like, 20 feet high and 5 feet in diameter. That's a lot of argon gas to let go. And what had happened, they had done all the stress analysis. This thing actually had a threaded steel closure here. They had done all their stress analysis on the supercomputer in the 1980s. That supercomputer would probably be a laptop today, right? But they had done their stress analysis on the threads, figuring the crack was starting to threads. What actually happened is this whole thing, because it's heated, this particular one had water cooling on the outside. Okay, the heater was on the inside and the water cooling on the outside to keep the pressure vessel cool. And they treated the water, but they had corrosion pits. Okay, the corrosion pits introduced hydrogen. It turns out the forging, which had been made in Japan, didn't quite meet spec on the first heat treatment, so they reheat treated it. Okay, and anyway, it's a long series of events, but the stress analysis was not done on the location where it failed, so they didn't worry about the stresses out here. It turns out it was transient thermal stresses. This thing being about 18 inches or 17 inches thick, where the fracture initiated, it takes 3 hours to get to temperature. This thing occurred after 2.5 hours. It was still seeing transient thermal stresses, which were higher than the operating stresses. So you had transient thermal stresses, you had material that wasn't up to spec. Okay, it's a long story about why it wasn't up to spec, and that has to do with you don't take the sample out of the final part. If you take a destructive test specimen out of the final part, you just destroyed your specimen, your part. So they had a small little part. Well, actually, maybe I will tell you this, because this is the type of thing you guys will run into. When you make a great big forging or casting like this, you'll leave some sort of little part on the side where you can take your mechanical test specimens. Okay? So the first time they heat treated it, they cut this thing off, and this thing was the exact same thermal processing as the great big piece because it was part of it, right? They just cut this little extra piece off, made their mechanical test specimens, tested it, found out it didn't have the right properties. So they said, oh, we got to reheat treat it. Well, you don't have a little thing like that to cut off anymore. So what you do is you just take another piece of material that's similar composition, and you just put it in the furnace next to it. Okay? But it's not as massive as that one. This might weigh 1,000 pounds. This one weighs 400,000 pounds. So they don't exactly heat up and cool down at the same rate. And so you just assume that this one went in the same furnace. You just sort of assume they all heated and cooled the same, except they don't. So this one way that a heat treater can get you to pass spec the second time. Okay? They test a different size part. Okay? That's accepted by the codes because it's not the only thing you can do with an extractable part. I've seen several failures because of it. But anyway, it turns out when they measured the properties of this after it had been destroyed, they found it still didn't meet spec. So lousy material properties, corrosion on the outside, corrosion generates hydrogen embrittlement. This thing should have had a critical flaw size of like 8-10 inches as critical flaw size before the thing would let go in a brittle failure. Because of all these different 4 or 5 factors, hydrogen, corrosion pitting, lousy mechanical properties, transient thermal stresses, all these things, each one of them keeps chipping away at that 8 or 10 inch critical flaw size and makes it smaller and smaller. I measured the critical flaw size at the origin as ½ an inch. Okay? You like to have something where the critical flaw size is greater than the thickness of the vessel if it's a pressure vessel, because that's called leak before break. You get a leak, and you'll hear the whistle, okay, or you'll see the spray, or whatever it is, before the thing goes kaboom. So you like to design something for leak before break, and this thing actually was designed for leak before break, but when you start stacking up all these screw-ups, okay, the critical flaw size got down smaller than the thickness of the vessel, and therefore, when it got to a critical flaw size, it just went kaboom, okay? What was really interesting to me in the whole thing was, you don't just go to the hardware store, Home Depot, and pick up another one of these vessels. Okay? It takes about a year and a half to build one of these things. It's a special, you gotta cast the steel, forge it, heat treat it, machine it, and all that could take a year or year and a half lead time. This was the world's largest unit, and they would have had to shut down aircraft production. If it were not for the fact that within 2 months they were about to commission the next largest one in the world, which was 64 inches in diameter. If they didn't have that one on order and about finished, we would have had, for a year and a half, we would have had a lot of aircraft engines, and would have had no spare parts, no new engines. Just think what that cost would have been to the world, right? So, it turns out, yeah.
How old was that vessel before it blew?
It was about 15 years old, or no, it was about 12 or 13 years old. Built in the mid-80s, and this all occurred in 97, 98 time frame.
What's a typical lifetime, like 50 years? Or?
Oh, well, no one could ever, this was the first one of this size. Typically, you talk numbers of cycles, and the number of cycles might be 20 or 30,000 cycles, heat treat cycles. And so if you're doing 200 a year, 10,000 cycles, yeah, I mean, you can get 50-year life if they design it for 10,000 cycles. But they go in every couple of years and they do a full, the ASME code, the boiler pressure vessel code, will require them every 2 or 3 years to go in and do a full non-destructive test, looking for flaws. And in fact, they had just done one like a year before. But they were looking on the threads on the inside, they weren't looking on the outside because they thought that was where the high stresses were. In static operation, that's where the high stresses were, on the threads. In transient operation, when the thing's heating up, turns out the highest stresses were over here. Okay? So, I remember coming back the second day I was there, came in, saw my executive officer, said, beware the transient thermal stresses. Okay? At that point, we didn't know about all the corrosion problems and everything else. But anyway, that's a way of diffusion bonding, if you will, on castings. But you have to get to a high temperature where you have enough temperature that the atoms will diffuse together. But the problem is you don't want to get to too high a temperature. And the reason you don't want to get to too high a temperature is because you get grain growth. And so if you look at the old version of the welding handbook on diffusion welding and brazing, they have a handy-dandy little picture here that talks about the problems. And lo and behold, they got surface roughness, they got oxide and contaminant layers on the metal. And this is characteristics of metal surface showing roughness and contaminants. Gee, we talked about that, right? I think we have. And here they have the 4 stages of diffusion bonding, as they call it. Initially, these are the grains in the metal, and these are the pores. And you have asperity contact. This is initial asperity contact. The first stage is where you've got pressure that squeezes these little touching mountain peaks together, and you get deformation, and so you get flat areas. And now you have pores, and you have a bond line here in the center, but you've got pores right along the bond line. And it says first stage deformation and interfacial boundary formation. So you had these grain boundaries here. Everybody know what grain boundaries are? You have different crystals of the metal. Okay, they all have slightly different orientation, and in between those you have what we call grain boundaries. So each one of these is a little single crystal grain, and you pack them all together, and where they come together, it's called a grain boundary. Okay, so this is the first stage. In the second stage, you actually have these grains start to grow, grain boundary migration and pore elimination. Some of the pores, essentially the vacancies, a pore can just be considered an inclusion consisting of vacancies, okay, lattice vacancies. So the vacancies actually can diffuse away at the grain boundaries. The grain boundaries actually act as sinks, okay. If I have a vacancy and it goes into a grain boundary, it just causes the grain boundaries to kind of collapse together a little bit, okay, and they kind of get smaller. So I get rid of some of the pores, but it turns out if a pore gets trapped, the third stage, if a pore gets trapped in the center of a grain and it's not in contact with a grain boundary, it'll stay there for 100 years. Oh, not 100 years, maybe 50 years at temperature. Okay? You got to have your pores in contact with your grain boundaries because the grain boundaries are the sinks for diffusion. Otherwise, those vacancies have to diffuse all the way through that crystal lattice. It might be might be 10,000 lattice rather than 1 or 2 lattice that you have to diffuse through. Okay? And so you tend to get third stage volume diffusion pore elimination, which takes forever. So true diffusion bonding stops here in stage 2. If you ever get to stage 3, it's all over. Well, the problem is, if you go to too high a temperature, the grains tend to grow as you get to high temperature. And so if you get above about 8/10 of the melting point, you go right past stages 1 and 2 into stage 3, and you'll end up with a bunch of pores in your interface and a weak bond. Okay? So you're limited at the low side in that you want diffusion to be fast enough. You're limited at the high side that you don't want grain growth. Okay? And so you have a fairly narrow range of processing temperatures that are tolerable for diffusion bonding. Okay. Another problem with diffusion bonding is you have a problem if you're bonding dissimilar metals. If you're titanium to titanium, there's no problem of dissimilar metals. But if I'm bonding two different materials, I've got a coefficient of thermal expansion mismatch, and I will set up residual stresses in that interface. So one of the problems I have, let's say I want to bond, we talked before about aluminum to steel as the transition joint for the superstructures for the Navy, and that's done by a cold welding process, essentially all at room temperature, and so it's going to operate at room temperature. There's no thermal expansion problem. If you bond it at the same temperature it's going to operate at, they don't have residual stresses. But if I were to heat that thing up substantially, the aluminum would expand faster than the steel, and the whole thing would bow. That's the bimetallic strip we talked about. That's my Faberwork pot, which is back there now. Remember, I didn't want 100% bond area. If that's 100% bond area, that whole thing would bow as the aluminum heats up, and the steel didn't heat up as much. Well, it turns out, if I look at the strain energy for bonding, there's a formula like this for plane stress. The strain energy goes as the width x squared, but the bond strength only goes, if this is unit depth, only goes as the width x. So if the residual stress energy goes as x squared, and the strength of the bond only goes as x, as the part gets bigger and bigger, I get bigger and bigger residual stresses. Okay? And even if I do it axisymmetric, it turns out the strain energy goes as r cubed, and the bond energy goes as the area, r squared. You always have one extra dimension to your energy as compared to your bond strength. And so larger and larger parts have more and more residual stress. And that's why, go all the way back to our silicon packaging, you don't have silicon chips bigger than about 1 centimeter square. And the reason is, if you go to 2 or 3 or 2 inch square, your residual stresses on that chip get to be unmanageable. Now, that's not to say you can't design fancy substructures that will allow for thermal expansion or try to match the thermal expansion of silicon. And it can be done, but it costs a lot of money. So in general, typically things with dissimilar metals, you don't like to have bonded areas more than about 1 centimeter on a side. And that's why the Faberwork pot, we don't want 100% bonded area of the aluminum to the bottom. We want some places where the thing can absorb some of those thermal strains and locally bow and change the shape of the pore a little bit to absorb the differential coefficient of expansion. Another problem, well, I see, let me talk about pressure. The deformation, so the temperatures are in that range. The deformation pressures are typically in the 500 to 5,000 psi range. I told you for HIPPY it went up to 10,000 psi, and that's because you can do it. But if I'm just taking two complex parts and squeezing them together in a great big hydraulic press to get the bond area, and let's say I got 2 turbine discs that are going to diffusion bond together, well, I'm going to have a 5,000 ton press with lots of square inches to be able to get these types of pressures. And in fact, one of your homework problems, I described at the time, probably still is, the world's largest diffusion bonding press. And I don't even remember what the numbers are, you can look at the homework problem. But Mitsubishi Heavy Industries built it to be able to diffusion bond and just make great big steel plates. Just like we talked about explosion welding. In this country, we use explosive bonding to slam two plates together, to clad one plate to another. Well, Mitsubishi Heavy Industries in the early 80s built this, I don't remember, 10,000 ton press or 50,000 ton press with a diffusion bonding furnace, so they could take great big, thick steel plates and bond tantalum or something to them. Okay, something else to them by diffusion bonding.
Just to understand the bigger picture, I guess, the diffusion bonding, the bond that it makes, is it just as strong as, say, a weld bond, or is it as strong as
A well-made diffusion bond is a near perfect weld. It is, in something like that titanium, you will not microscopically be able to find the joint. It is indistinguishable from the surrounding material, in the right material. Okay, and that, so it is better than a fusion weld. It's a near perfect joint. Okay, it's as close as we come to a perfect joint. The problem is, only certain materials will dissolve away. Another criteria is we got to diffuse away our contaminants. Okay, well, it turns out iron, titanium, and nickel, and to a certain extent copper, relatively easy to get a near perfect bond. Okay, talking about diffusion bonding here. Things like aluminum and magnesium, very different. Okay, and the reason is iron, titanium, nickel, and copper will dissolve their own oxides. Iron will dissolve oxygen. So if I have an iron oxygen surface contaminant, it'll just diffuse, the oxygen can diffuse away into the iron, and the contamination doesn't have to be extruded out of the joint. In cold welding, I have to extrude the contamination out of the joint. If I do ultrasonic, I'm just kind of moving it aside, and I'm burying little islands of contamination. I never get a perfect joint. Okay, but titanium loves oxygen, and it will dissolve away its own oxide wonderfully. Titanium is probably one of the easiest materials to diffusion bond. Nickel will diffuse away some oxygen. It's not the easiest, and copper as well. So they can be diffusion bonded relatively easily. Titanium is the easiest, next to iron, then probably copper, and then nickel. But they're all relatively easy because they will diffuse away, well, iron will also diffuse carbon, so will titanium. Titanium will diffuse away almost anything. Carbon, nitrogen, oxygen, any type of contaminant you can think of on the surface. Hydrogen, titanium loves it, okay? Iron will diffuse away all those things. Carbon, if I have CO2 on the surface, okay, or CO on the surface, it'll diffuse into the base material. Nickel doesn't diffuse carbon, okay? So I got to have something else in that nickel alloy, and many of the things that are in those nickel alloys will take up the carbon, but pure nickel doesn't like carbon. Okay, copper doesn't like carbon, so that's why these two are a little bit harder than those two. But generally, you can diffusion bond all four of those. The problem here: aluminum and magnesium both melt around 650 centigrade, 650, 660 centigrade. Their oxides melt at 2,000 to 2,800 degrees centigrade, and they don't dissolve oxygen in the middle. So you can push these two pieces of aluminum together till you're blue in the face, and you'll still have an aluminum oxide layer. Okay? You can go above the melting point. In fact, if you've ever seen aluminum melt in a fire, it actually sort of sags and it has its own skin, aluminum oxide skin. Okay? The aluminum oxide still has strength and will actually support the liquid aluminum on the inside for a little while. Okay? When you first get melting. So these can't be diffusion bonded, but it's very difficult. Now it turns out I actually have a piece of aluminum that has been not exactly diffusion bonded, but almost. The first day of this class, I think it was the first day of this class, we had class, no, it wasn't your class, it was the other class I was teaching before you. I had to go up to Montreal because this company, Novellus, which used to be part of Alcan Aluminum, introduced this new product, people have been using clad aluminum plates for years. And one of the problems with high-strength aluminum alloys is you might put 4 or 5% magnesium. 54, 56 aluminum alloy is what the Navy uses for hydrofoils and things like that. Has 4 or 5% magnesium. The problem with 4 or 5% magnesium, good strength, but lousy corrosion resistance. But nobody knows more about corrosion than the Navy, right? And how to try to control it, maintain it. You've got lots of semen, scrape things. Okay. Anyway, for years and years, people have been cladding aluminum plates in the rolling mill with relatively pure aluminum. Pure aluminum has fantastic corrosion resistance, but has lousy strength. So they basically make a clad structure, and in fact, for years and years, it's been called, the trademark was called Alclad for aluminum clad plate. Okay, so you can buy Alclad. Every big aircraft skin you've ever seen is Alclad sheet. It's got about 5 to 10 microns of pure aluminum on the surface of a high-strength aluminum alloy. Problem with a high-strength aluminum alloy, a little bit of moisture will cause stress corrosion cracking. Okay, but you know, if you clad a layer that's maybe not even as thick as paint, but perfectly welded to the surface, and you don't scratch through it, there's no problem with it. And you don't like people coming up and scratching your nice American Airlines jet, nice shiny jet, right? Well, basically what Novellus has invented is a way to co-cast. In fact, they originally called it co-cast, now they call it fusion, because the marketing people came in to give it a name. But they call it co-cast, and you originally cast these great big aluminum ingots. They weigh about 20 or 30,000 pounds. They might be about 3 or 4 feet wide, and they might be 6 or 7 feet in the other direction by about 30 feet high. So great big slabs of aluminum that you're going to roll. In the old days, they had to roll some pure aluminum plate, and they might roll it down about 1 inch thick. And they would cut it up, and they'd have a guy come along with an arc welder, and he would weld this plate, this 1 inch plate, to this great big 3-foot slab of the high strength alloy on either one or both sides. And then they would put it through the rolling mill, and essentially it's not cold rolling or cold welding, it's sort of warm welding. It's got a little heat to it because you got to deform the aluminum. But basically you're trying to do essentially a cold welding or a warm welding. And every now and then one of that top 1 inch layer would just peel right off and you produce scrap. With this, you cast everything together. You don't have to roll the corrosion resistant layer down to 1 inch, because you're going to cast it 1 inch thick. Okay, and then you don't have to weld it. It's already bonded, and then just put it straight in the rolling mill, just like any other slab. So tremendous productivity advantage. And now the question is, are they going to sell it for the premium markets, like the aircraft markets, or are they going to get it into the automotive markets to try to get Ford and General Motors and everybody else to give them a premium price for a product that really doesn't cost them much more to make than the regular old aluminum? Okay, so now this is a business question of who extracts the profit from this new technology. But in any case, they had an announcement up in Montreal at a World Aluminum Conference a couple of weeks ago to announce that technology. Essentially, a diffusion bond where I end up getting to the point, and I won't give you all the details of it, but I have this lower alloy aluminum, or high alloy aluminum, I'm sorry, high strength, we'll call it aluminum mag alloy, and I'm going to cast actually a slightly higher melting temperature pure aluminum on it. And I can do it on both sides if I want. But it turns out, by the way you design your furnace and everything up here, you actually, by radiant heating, sort of melt a very, very thin layer of this. And so when this stuff comes up, you actually just kind of peel back that aluminum oxide skin. As this liquid floats up, the aluminum oxide floats off on this. And in fact, you can write, when this stuff is solidifying, you can actually write something, and you just take a steel rod, and you can write, in fact, you can write MIT in the aluminum. The aluminum oxide skin, you can just write your name. I mean, I've done this when they're casting. You can write your name in here, and when you finish, that distorted name in the oxide, the distortion of the surface oxide here, will actually be found on one of the final surfaces where the oxide is, because you're just floating the oxide away. Okay, that's the case where you're floating it away, and you actually have a very thin liquid layer of aluminum, and you're essentially getting a diffusion bond in the casting process. Okay, so neat technology in some ways. Okay, so let's talk about a couple of experiences. Well, actually, I haven't talked about transient liquid phase bonding yet. I have to hold those experiences for next time. We got to talk about TLP first. So one of the problems with this, big clamping furnaces or fixtures, or putting them in pressure vessels full of high pressure argon, and that's a pain, and it's also expensive. Another problem that I didn't mention here is you want to avoid brittle intermetallics. Some of these things, like if I try to bond aluminum to titanium, well, even if I solve the problem of getting rid of the aluminum oxide, and actually titanium probably would, I tend to form titanium aluminides. There are various ones. And they're brittle intermetallics. And I can end up with a brittle intermetallic at my interface. So one way to get around this problem is you could nickel plate your titanium before you try to bond the aluminum to it, except there's nickel aluminum intermetallics, but they're not as bad as the titanium aluminum intermetallics. Okay, but you like to find certain type of systems where you don't have brittle intermetallics. So diffusion bonding only works for certain systems, certain alloys, and if you do dissimilar bonding, only certain systems. So, and it's also very expensive. So you don't use it for cheap things. You don't diffusion bond ships. Okay? Can you imagine a fixture to squeeze a ship from 10,000 psi or 5,000 psi? Okay, I'm sure you guys can figure out how to put 5,000 psi on a ship for a very brief period of time, but it's probably not good for the ship. Maybe the enemy would do it for you. In any case, the next thing that people did, and actually it was started in the 1950s, but Pratt & Whitney registered a trademark in 1972 called TLP for transient liquid phase. And TLP bonding, what they did originally, they had nickel-based superalloys. I actually think they discovered this by accident. But anyway, to another nickel-based superalloy. And if you put a nickel-boron alloy in between, boron lowers the melting point of nickel substantially, several hundred degrees centigrade. And actually, we use nickel-boron alloys as brazes. I could make a braze joint between two pieces of nickel with a nickel-boron braze alloy, which melts at a lower temperature. And if I hold it at the brazing temperature, not for a couple of minutes while I'm making the braze, but for a couple of hours. And I'm not talking about 24 hours like a typical diffusion bond. I'm talking about maybe 2 hours. I can diffuse the boron away and leave behind relatively pure nickel here. And I essentially raise the melting point of my liquid. So it's a transient liquid phase. I heat it up to the point where I get a liquid between my two solids, but I diffuse away what we call the melting point depressant. Okay? In this case, the melting point depressant is boron. And if I diffuse it away to the base material, I will raise the temperature, and I end up with something that's called isothermal solidification. Now, we know solidification right now. I take a liquid and I cool it down. As I drop the temperature, this is called athermal solidification. I drop the temperature, it solidifies. But I can also go across the two-phase phase diagram, and how many of you even know what a phase diagram is? Temperature versus composition. If this is nickel and boron, it turns out the nickel-boron phase diagram might look something like this. Boron goes way up. But I have liquid, I have solid nickel with a little bit of boron, and over here I might have solid boron. This is the melting point of nickel, pure nickel. This is the melting point of the alloy. This is the braze alloy. It's lower. This type of phase diagram, this basically shows on a temperature composition map between nickel and boron how I lower the melting point by adding another thing to it. Another diagram that looks very similar to this that you know of, and some of you who lived in the north have already used in your life, is the Ice Salt Biograph. Okay? You throw salt on the icy sidewalk, you've got solid ice, which melts at 0 degrees centigrade, and salt water, you guys should know this, melts at a lower temperature than 0 degrees centigrade. Depends on the salt concentration, okay? But you will form what we call eutectic, okay? And eutectic is Greek for low melting. At a certain composition, if you've ever made your own ice cream, if you live in the South, you put salt on the ice in an ice cream freezer, and that's what lowers the temperature, and you extract the heat of fusion from the salt water. And that extraction, actually you absorb the heat of fusion as you melt the salt water. It has to absorb the heat of fusion. It takes it out of the cream, and you freeze the cream. Okay? So it's the same type of phase diagram. And what we're doing is in regular solidification, I have the same composition, and I just lower the temperature, and I freeze by going down in temperature. In TLP bonding, I keep the same temperature, and I go across the phase diagram, going from the liquid region to the solid region by changing the composition. The boron diffuses away, I change the composition of the center. And just to finish this up, you have a handy-dandy paper, TLP with an asterisk to tell you that it's a trademark, okay? This is a 1973, I think, Welding journal paper, written by the guys who supposedly invented this, Duval, Zarsky, and Polonis. And here, on figure 17, is the diagram, the detailed diagram of what I was just discussing, sort of. Okay? Just to finish up TLP for today. I have a liquid between two solids. The composition is very rich in boron in the liquid and no boron in the solids. This is the phase diagram. No boron, everything solid. I add boron, I have this type of phase diagram with this amount of boron, C1. And so this is liquid, this is solid at this temperature. As I heat it, I actually will dissolve some of the parent metal, and the bond will get thicker, and my center composition will be the same composition as what sits on this line, and I'll start to diffuse the boron away. If I hold it there for a long period of time, that thick liquid region, as the boron diffuses away, will get thinner and thinner. Eventually, I will end up with a virtually perfect bond. Almost, there is still a small compositional variation that I can measure, but you can't see it in the microscope.
As you're holding it, as you're waiting for the diffusion of boron, are you also increasing the temperature so?
Nope. You
let
could,
it
but
slow
you
down?
don't have to. And we don't usually have to get that fancy.
So that's actually it's not like a brazed joint anymore. It's like a weld.
You're making a weld at low temperature. I would say it starts as a braze and ends as a weld. But you don't have to raise it up to high temperatures. In fact, what we're doing right now for Intel is we're making solder joints with indium tin at 75 degrees centigrade. Typical solder joints for lead tin solder are 183 degrees centigrade. Well, the problem with, if I wanted to get good metal-metal attachment of the silicon to its substrate to get good thermal, heat transfer, I'd like to get a good metal-metal joint, but I don't want to do it at a very high temperature. If I do it at a very high temperature, I get residual stresses from the thermal expansion problem, right? If I can do it at lower temperatures, I have much lower thermal stresses, residual stresses from the thermal expansion. So I'd like to make the joint at low temperatures, but if I make it at too low a temperature, then when it heats up later in operation of that chip, because some of those chips might operate close to 75 degrees C when they're really humming along, the joint will come undone if I just solder it with a low temperature solder. What we're doing is we're doing what's called low temperature transient liquid phase bonding form, where we actually are developing alloys where we diffuse away. You can make the joint at 75 degrees C, and you diffuse it long enough, and we're trying to do it in less than 2 hours. In fact, we can do it in less than 2 hours. So they actually have to soak this thing for 2 hours at 75 degrees C, but it might operate for 1,000 hours at 75 degrees C. So that's within the realm of possibility. But it turns out it won't remelt until about 300 degrees C after we've diffused away the melting point depressant, which means it has fantastic strength after you've held it at temperature. So we end up making a weld by soldering at low temperature. Okay? So Intel's actually coming next Wednesday to review this, or Thursday. Anyway, so, and I'll tell you another story about, for you sub guys, about how we saved 3 transformers for the nuclear control rods of the Navy subs that they thought they had scrapped $3 million, or $1.5 million worth of transformers, $500,000 apiece. And Raytheon called me in and I said, oh, you get up with a transit liquid phased solder joint. And I wrote a letter, attached this paper, and the Navy guys signed off on it and accepted it. I'll tell you that story next time. Okay.